All right, so we're going to do the electrochemical series, and we've set up the well plates here. And up top we have magnesium, a little piece of magnesium in each well. Right here we have a little piece of zinc in each well, and then here we have some copper in the wells. And to that we're going to add a solution of magnesium. It's magnesium sulfate, but the sulfate doesn't matter. We'll have zinc sulfate here, we'll have hydrochloric acid, copper sulfate, and then silver nitrate here. And each one of these solutions is going to be 1 molar, and we'll see if there's a reaction. And if there's a reaction, we'll know where to place them on the electrochemistry series. So there's the magnesium. And we'll add the zinc solution. Hydrochloric acid. This one might bubble things a little bit, so watch for that. That one's bubbling. You can see there that the hydrochloric acid is definitely reacting with these magnesium, and it should react with the zinc, but it might take it a little bit longer. And there's the copper. We'll check back in on that in a little while.
I do see bubbles in the zinc.
Let's see here.
It's hard to see on camera.
There's a few little bubbles there forming. Let me finish adding the other 2 solutions here. So here's the copper. That one's definitely reacting with the magnesium. And then silver. For whatever reason, I always get a little bit of this on me. So a color change and bubbling is usually a good sign that there's a reaction. And then I'm also seeing some copper plating onto the zinc here. So, and we shouldn't expect copper to react with itself. So I also saw some bubbling when I added the silver to the magnesium. And we see some for the zinc right here. That one's bubbling a little bit. And then you notice how the copper is changing color with the silver solution there. And here, let me poke it a little. There we go. See how it changed color? That's because the silver is reacting and being reduced and plating onto the copper. So a little bubbling there on the magnesium with the zinc. The hydrochloric acid is almost completely eaten this magnesium up. Copper definitely had a reaction with the magnesium, and silver did too. And if we look over here, no reaction, of course, with magnesium with itself. And then we look, definitely a reaction between the zinc and the hydrochloric acid. We have a reaction between the copper and zinc, copper solution and zinc metal. And definitely reactions there. So yeah. So we might check back in on this at the end, and I'll probably take a picture of it because sometimes that's easier to look at. But let's explore a reaction between the copper and zinc a little further. We're going to make a Daniell cell. Now earlier I made a salt bridge, and salt bridge is necessary to complete the circuit. So I've got that set up over here. Let's just adjust this a little bit, like that. So right here I've put the zinc solution. This is 1 molar of zinc sulfate in this left test tube, and I've added the salt bridge in so that it will complete the circuit. And then over here on the right side I've put in copper. Now I did that on purpose because convention states that the anode should be on the left side and the cathode should be on the right side, and I'm trying to follow convention as much as possible. So since we have the zinc is the anode, convention also says that the negative terminal, which is the anode, is the black wire. So I'm just going to add this, and this is a zinc piece of metal here. I'm going to put that down in this solution here. And then convention says that the positive wire is red, and I've got a copper wire on that. So I'll stick that in that solution. And then if we come over and look at our voltmeter, we can see the voltage is 1.065 volts. And that should match up pretty well with our standard potentials, because both of these solutions are 1 molar and standard potentials are measured at 1 molar. So that's that first one now. Now, beyond verifying that our standard potential charts work, let's do an unknown solution of copper. So I've got some right here. We don't know how much is in there. I guess the stockroom knows, but they didn't tell me, so we're going to have to measure the concentration. So I put some in a test tube here, and what I'm going to do is replace this one that has the copper solution that we know the concentration of with this one. So let's take this out, and we'll need to rinse off our salt bridge so that we don't contaminate the solution. So got that rinsed off, and then we'll replace the cathode tube with the unknown solution. And let's see what the voltage says now. So put that in, and now it's reading 1.06, probably 0.5, because it's kind of alternating between 0 and 1. So you could probably estimate that. Now, you'll notice that the voltage didn't change that much, even though we probably changed the concentration quite a bit. And you can tell that just from the color of the solutions. Copper solutions have this blue color, but this one, I suspect, should be much lower in concentration just because the color is not as strong. But you'll notice that the voltage doesn't change that much. That's just a property of how the Nernst equation works with, once you start adding logarithms in there, that can really affect how much change there is.
How much was it with the 1 molar? 1.06?
6.7,
Oh, okay.
I think. So we can check.
That's fine.
But usually they don't change that much.
Right.
It's such a small change, and you're like, oh, that's it. But the change in concentration can be pretty dramatic with a small change in voltage. So I put the other solution back in. I didn't bother rinsing it off because we're just checking real quick. But 1.075. So no, there is a little bit of a change. 0.015 change, maybe somewhere around in there. So, all right. Now, it's not in the lab manual, but I do have a piece of silver, and we have silver solution. So I think we'll set up another cell, but this time we'll use a silver solution. Now, let's see here. Silver will reduce in the presence of copper. We know that from our well plate over there. So if we use the copper electrode, that will be oxidized, so we'll need to put the copper on the left side, we'll put the silver on the right side. That way we'll change it so that now it's the anode. So we're going to need to rinse off our salt bridge again, because silver sulfate is insoluble. I don't want that contamination. We might still get a little bit of precipitation from the silver, just because the salt bridge is made of potassium chloride. But
I was gonna say, this is not gonna fit in the tube. What was the solution again? But there we
we're
go.
gonna put it in the beaker.
Mhm.
Yeah. So since the copper is going to be the anode now, I'll switch the copper wire over to the black alligator leads and get that in, and then we'll have the silver. Now this is a silver electrode that I've added to by electroplating it, so that's why it has all these like little crystals of silver on there, which is kind of cool. It was really foaming when I made it before.
So can we make jewelry with electrolysis, Dr. Wilson?
I think so. Now, I don't want to use a lot of silver because this stuff is one of those semi-precious metals. So I'll just try to use a small amount, and I'll probably have to, we'll probably have to kind of hold this carefully here. So we just need the electrode to touch the water, and then we'll need the salt bridge to reach down in there too. Something like this. And that should work. And we're getting 0.501 or half a volt roughly there with this cell that we have there. So just another different kind of battery. And actually, as we wait here, I'm going to be adding a minute quantity of silver to my electrode, so I'm not really losing it because we are doing reduction in this side of the reaction, and we're doing oxidation over here. So a very tiny amount of this copper wire is dissolving into the solution, making copper 2+, and a small amount of the silver is being reduced onto the electrode. Now we're running a very tiny amount of current through this apparatus, so if you weighed them before and after, you wouldn't notice any difference, but a tiny amount will be reacting. So let's get this out. And you can probably see there's a few little spots under there. That's probably silver chloride because we had potassium chloride in this. And as you know, silver chloride's an insoluble salt, so we just precipitated a little bit of silver by doing that, which I suspected would happen. So, yeah.
Very nice.
Now, is there anything else that we need to do for the lab? I think that's what we wanted to cover. We should check back on our well plate just to one final check. Sometimes the reactions are a little slower, so we'll just make sure. So we can easily see the bubbles on the zinc now. That was something that I really wanted to make sure showed up on camera. And I don't really see a reaction between the zinc solution and, well, zinc and zinc solution should not react with itself. And I don't see a reaction between the magnesium solution and the zinc, which should be expected because we do see a reaction over here, and this would be the opposite reaction. So this is where magnesium's being oxidized by zinc. If it was reacting over here, that would be zinc being oxidized by magnesium, and these both can't happen at once, so it makes sense that there's nothing happening there. And then as far as copper reacting, we shouldn't see any reaction until we get to here. And we would know because these solutions would start to turn blue, or kind of a gray-green in that case. So, good.
Dr. Wilson, can you predict the results of this activity series right here in the well plates?
You
Without
can,
actually doing it?
by looking at the activity series chart. And so, if I happen to have one right here. And if we look, let's move these out of the way here. Let's see if we can find some of these reactions. So here's zinc, negative 0.76 is down there. And where's another one that we tested? We have copper up here, right? It's 0.34. So we should be able to, from this, tell that the copper must be the cathode since it's higher up on here, and the zinc must be the anode, because if we take 0.34 minus 0.76, that's a positive number, and that means that the delta G would be negative. So that's one way to predict whether a reaction would happen. So in this case, we can tell that the zinc will react with the copper solution, but the copper solution will not, but the zinc solution will not react with the copper.
So basically the half reaction that's lower down on this standard reduction potential table essentially is flipped. So you change the sign
Right.
and then add them.
Mm-hmm. That's one way to do it.
Mm-hmm.
So if it's not clear, you can verify using one of these charts. But of course, these charts were made by measuring a lot of different reactions, and they were all based off of measuring the standard hydrogen electrode reaction, which is the reduction of hydrogen to H plus to hydrogen, and that's defined as 0 volts. We picked that because it's very much in the middle of this range, and we didn't want to pick something that was all the way at the top or all the way at the bottom in case we discovered something that was either a stronger oxidizer or a stronger reducer. So we wanted something in the middle.
So the things that are down lower are more active, is that the way you say it, than the ones that are above? Because here's a sample of an activity series on the chart as well. I see lithium is more active than potassium, which is more active than iron. So it seems like these down here, you can say they're more active, right?
Yes, the metals here will react to reduce things up top.
In other words, they can
They're
displace,
stronger reducing.
right?
They will cause reduction in something else. They will themselves become oxidized, but they will release their electrons to other species.
And reduce them.
Mm-hmm. That is why, since magnesium is really far down on the chart, that it reacted with all of the other metals, because all of the other metals are higher up on the chart. So for example, magnesium's way down here, zinc is up a little bit higher, so that's why we saw a reaction with it.
So hopefully they can get this all on one page. I think they can do it, especially if you use a pencil. You can erase and fit it all on one page, and
Yes.
we can help you to get this done if you get stuck or have questions.
And we'll also upload some pictures to go with the video, because sometimes it's easier to just look at a static image of the results of the plate, and we'll get that information included on Canvas.